Where do the formulas for the volume of a sphere and the volume of a cone come from? Let's prove it. So, volume of a sphere, of course, being the classic 4/3 pi r cubed, and then the slightly less easy to remember formula for a cone, which is 1/3 pi r squared h. Now, you are probably vaguely familiar with these formulas from GCSE, or at least if you're a student in England. But I must admit, it's one of those slightly odd aspects to the English education system where you're taught what these formulas are, you're then effectively shown how to mindlessly plug numbers into these formulas to get then the volumes that you need. And then after that, they don't really ever appear much again, which is a bit unsatisfying.
Why?
But I can kind of understand why. Ultimately, it's one of those classic things of, I guess I could use the analogy, you don't need to be a car mechanic in order to be able to drive a car. You don't need to know why something works in order to just be able to do it. So, that's a bit unsatisfying. We're going to be correcting that issue today because we're going to be proving these formulas. But before we do, the usual reminder. Yeah, you don't need to know these proofs off by heart for the A-level exams, though it's worth pointing out that actually, I think from memory, volume of a sphere the proof of it did appear as a question in a further maths A-level paper one year, but that was just as a sort of one-off question on the spot sort of thing. You weren't expected to go into that already knowing how to do that proof. Anyway, how are we going to do it? Well, in order to be able to do it, you're going to need to be able to use volumes of revolution. Both volumes of revolution are formed by rotating a region about the x-axis, and also today we're also going to do it by rotating a region about the y-axis as well. The formulas for which are respectively on the screen right now. If you don't know how to do volumes of revolution though, I do have a tutorial video explaining it. So by all means, if you would be interested in knowing how this proof we're doing today works, then do have a look at that tutorial video to first understand what volumes of revolution is. Right, let's start off with the volume of a sphere. In order to do this, we're going to start off with a circle. A circle with a center of 0, 0. That doesn't really matter so much as long as the center is on the x-axis, and it's a circle with a radius of r. And therefore that'll have the equation x squared plus y squared equals r squared. We're then, for the purposes of what we're going to be doing, wanting that to be in the form y equals. So doing a bit of algebra rearranging to make y the subject of the formula, you will end up with y equals the square root of r squared minus x squared. Technically, there should be the plus minus in front of there of the square root, because if we don't have the plus minus there, then what you're ending up with is just half of the circle, specifically the top half if you have the plus version of the square root. However, that's actually going to be fine for our purposes today, because what we're going to do is we're going to rotate that region that's above the x-axis about the x-axis to then form the sphere, the volume of the sphere that we need. So that's the formula we need, the equation we need. We're then going to also need to know what the x-intercepts are, because they will form the limits of our integral. Couple of different ways you could do that. Either just use the logic that you know the radius of the circle is r, so therefore logically you already know where the x-intercepts are going to be. Alternatively, you could find them manually by doing the classic thing of saying y equal to 0 and then rearranging. So you get x squared equals r squared, and then therefore x has got to equal plus or minus r, and so therefore those are our x-intercepts, and they will also form the limits of our integral. So then, therefore, the volume of a sphere by volumes of revolution rotating about the x-axis, 360 degrees, will be pi lots of the integral of our equation for y, all squared, and then we're going to do that integral from minus r to r, our two x limits. So straight away, really nice thing, although we've got the horrible square root in there, it doesn't matter because the squared and the square root are going to cancel out, meaning we're just integrating r squared, take away x squared now. Worth pointing out also we're integrating x's. So then we can actually start doing that integration. R squared looks a bit scary, but r is just a constant for the purposes of this proof. So this is no different to integrating just 2. 2 would integrate to 2x, so therefore r squared would integrate to r squared x. And then the takeaway x squared will integrate to the classic minus 1/3 x cubed, the normal add 1 to the power, divide by the new power sort of trick. Then we can plug the limits in. So if we plug r in, we get quite simply r cubed, take away 1/3 r cubed. And then plugging in minus r into there. Be careful, of course, that is going to be minus r all cubed. Admittedly, because it's cubed, you'll get away with bad notation here, because as it happens, minus r cubed is minus r cubed, because a negative times a negative times a negative is a negative. So therefore, replacing that in there, we've got minus r cubed, which therefore will become positive 1/3 r cubed, because that third was at the front as well. Okay, simplifying the expressions inside those two mini brackets, and you will find enough in both cases end up with a 2/3 r cubed, except in the second one you end up with minus 2/3 r cubed. But wait a minute, we've got a minus there, so therefore that could be viewed as a positive 2/3 r cubed plus 2/3 r cubed. And oh my goodness, you can probably see that therefore that is where the 4/3 comes from. So there you go. Boom, we have proved that the formula for the volume of a sphere is 4/3 pi r cubed. Nice, one of the proofs already done. Onto the proof of the formula for volume of a cone. To do this, we are going to use a straight line to do this. And I'm going to use specifically the equation of the straight line, y equals minus h over r x plus h. Now, admittedly, that might be a bit unusual compared to other proofs for this you may see, because normally most people will be lazy and do volumes of revolution about the x-axis again, and therefore have a diagonal straight line that looks something like that. And therefore, if you rotate that about the x-axis, the cone will be formed in that sort of way that you can see on the screen right now. However, for no mathematical reason, just purely from a visual sort of preference, I prefer the cone to be sitting on its base, and therefore I'm going to be forming the volume by rotating about the y-axis. So therefore, that's why I've chosen my equational line, because that looks like this. It's a straight line with a y-intercept of h, we can see clearly straight away from the equation. And then the x-intercept, well, set y equal to 0 and manually rearrange. So move the minus hr over x, minus h over r, lots of x, onto the other side. Then divide by h over r to get x equals r as our x-intercept. That means if we rotate this region about the y-axis, you will end up with a cone that's got a height of h and a base of a circle with a radius of r, which is exactly what we want. Worth pointing out that h and r are going to be constants for the purpose of this proof as well. So that's important, but if we are doing volumes of revolution about the y-axis, for the formula, we need it to be rearranged to be x as the subject of the formula before we can use that equation. So doing that, we can basically move the h onto the other side. Then we can divide both sides by minus h over r, which will end up with that. But of course, you could then multiply out the brackets, which means you'll end up with the equation being x equals minus r over h, lots of y, plus r. Brilliant. It's now in the format we need. So now we can start getting on with the volumes of revolution. So that will be the formula, pi lots of the integral of x squared, integrate with respect to y, and then our limits, be really careful because we're integrating to find the volumes of revolution rotated about the y-axis. The limits we're going to be using are y values, so that's why I'm going from 0 to h, because that is what was on the y-axis before. So, multiplying out the brackets first, being really careful with that, you will end up with r squared over h squared, lots of y squared, minus 2 lots of r squared over h, lots of y, and then the plus r squared on the end. That looks a bit scary, but as I said, a reminder, r and h are just constants, so it's really not as bad as it looks. So integrating it, the y squared will become a 1/3 y cubed, and then we still got that coefficient of r squared over h squared as well, combining with that third. We have the y integrating to a y squared with a half in front. That half will then cancel out with the 2 that's in the original coefficient of minus 2r squared over h, leaving us with minus r squared over h. And then, of course, just like before, r squared is just a constant, so it's going to integrate to r squared y. Nice. Then we can plug in our limits of h and 0. So plugging in h, just going to have the expression we had above, but with h's in place of y. And then plugging in 0, normally, good teaching point would be to point out that be careful, don't just always assume plugging 0 into something will lead to 0. But in this case, luckily it does. So it will work out very nicely there. So I can just take away 0 for that limit. Then, of course, we can do a bit of tidying up. You'll notice we've got an h cubed divided by an h squared, which is just an h. We've got an h squared divided by an h in the second term, and that is just an h as well. So we're going to end up with what you can see there at the bottom. But wait a minute, we've got a minus r squared h and a positive r squared h. And what do you know? They're going to cancel out to leave us with just 1/3 pi r squared h. Oosh! There you go. Formula for the volume of a cone also proved for you right there. Nice. So, hopefully you found today's video interesting. On the screen right now, you'll see links to some of the videos in my other series, like the Can We Do That series, as well as also a link to another video in this Prove It series. Goodbye.